This wind turbine runs quieter than the conversation you're having right now. It almost never kills a bird, and in some documented homes, paired with a few solar panels, it has pushed energy self-sufficiency past 90% across a full year. It does all of that by borrowing a shape that is more than 2,000 years old, a spiral that an ancient Greek mathematician drew to move water uphill. And here is the strange part. You have almost certainly never seen one spinning on a roof, and you probably never will. So what is going on? If something is this quiet, this safe, and this efficient, why is it nowhere? If you would rather understand how a machine actually works than just accept the loud, three-bladed one everybody pictures, stay with me and think about subscribing, because chasing down exactly this kind of overlooked engineering is the whole reason this channel exists. What you're looking at is called the Archimedes wind turbine, and to understand why it works, you have to go back to the 3rd century BC. The king of Syracuse, Hiero II, commissioned the largest ship of its age, a vessel so big that water leaked into its hull faster than a crew could bail it out by hand. So the king turned to Archimedes, one of the sharpest minds the ancient world ever produced, and asked him to solve it. What Archimedes built was a spiral blade sealed inside a cylinder. Turn the handle, and the spiral walked water up and out of the hull, defying gravity with nothing but geometry. The same device showed up in Egypt, lifting Nile water into irrigation channels, and later in Roman mines, pulling groundwater up from deep underground. For more than 2,000 years, the Archimedes screw stayed the best way humanity had to move water with the least possible labor. Then, in 2003, a Dutch inventor named Marinus Miramet asked a question nobody had bothered to ask. The screw uses a person to move the fluid. What happens if you let the fluid move the screw? He had noticed a gap in Archimedes' own surviving work. The old master had worked out the volumes of shapes spun around an axis, but he had never explored the three-dimensional spiral as a rotor, as a thing that could be turned by something pushing on it. So Miramet reshaped the screw into a cone, a spiral that opened outward, designed for the one kind of wind everybody else had given up on. The messy, swirling, direction-changing wind that tumbles across a rooftop. The first patents landed in 2006. After a decade of testing, manufacturing began in South Korea in 2016, and the result got a name, the Liam F1. To see why that shape matters, you have to understand why the wind turbine you already picture fails in a backyard. A standard three-blade turbine works on lift, the exact same force that holds up an airplane wing. It needs smooth, fast air flowing cleanly across thin blades to build the pressure difference that spins it. Below roughly 9 to 11 miles an hour, it produces almost nothing, and every time the wind shifts direction, the whole heavy machine has to swing around to face it, burning energy just to reorient. Now think about where your house sits. In the layer of air below about 30 feet, right where a rooftop turbine lives, the wind does not flow smoothly. It stumbles, gusts, and changes direction every few seconds. A conventional turbine dropped into that mess just vibrates, thumps out that rhythmic noise the neighbors complain about, and slowly shakes itself toward failure, all without making any real power. The Archimedes turbine throws out the airplane wing entirely. Its rotor is 3 circular blades wrapped around each other and stretched along a horizontal shaft into a cone, a spiral modeled on the Fibonacci sequence and the curve of a nautilus shell. Instead of building pressure across the thin edge of a blade, it builds it through the whole volume of the spiral. Wind enters the wide mouth of the cone, gets squeezed and accelerated along the curving surface, and is bent a full 90 degrees as it passes through. And in that bending, the turbine strips out a huge share of the wind's energy, and that single geometric trick gives it 3 abilities a normal turbine cannot match in a city. It aims itself into the wind with no motors and no sensors, because the spiral is naturally balanced. It keeps working even when the wind hits it at an angle as steep as 60 degrees off-center. Exactly the swirling kind of gust that stalls a conventional rotor, and it begins making usable power at just 5.5 miles an hour, while its bladed rivals are still standing dead, waiting for 11. I'll admit, when I first read that a turbine could aim itself with no electronics at all, I assumed there was a catch buried somewhere in the engineering. There isn't. The balance is just a consequence of the shape. The cleverness was spent 2,000 years ago, and this is simply someone finally turning it inside out. And the theory holds up when you put real instruments on it. The manufacturer claims the Liam F1 captures about 80% of the BET's limit, the hard physical ceiling on how much energy any turbine can pull from moving air. Independent researchers, running the numbers more cautiously, land lower than that headline figure. But even their conservative results put it at roughly double the efficiency of a conventional small turbine. The most thorough outside testing came from Pusan National University in South Korea, including a site on the typhoon-battered coast of Incheon. There, the rotor started itself reliably in light wind, ran steadily through turbulent and shifting air, and came through conditions that would have torn a normal residential turbine apart, with no structural failure. And in real homes that paired it with solar panels, annual self-sufficiency climbed from 61% on solar alone to over 92%. Almost all of that gain arriving in autumn and winter, exactly when the sun stops pulling its weight. Then there is the quiet, which is not a small thing. A conventional turbine of similar size hits about 65 decibels, carrying that signature thump made by air being sliced off the tip of each blade. The Archimedes design has no blade tips to slice with, so it runs below 45 decibels at full tilt, about the sound of light rain, under the level of an ordinary conversation. And because it turns as a slow, solid, visible mass instead of vanishing into a high-speed blur, birds and bats see it coming and steer around it. Across more than a decade of testing, from the Dutch coast to South Korea, bird strikes on these spirals are recorded as essentially zero. If a self-aiming, bird-safe, 2,000-year-old spiral is the kind of thing you had no idea existed, that gap is exactly what this channel goes digging for, and one quick subscribe is the only signal that tells the algorithm to keep handing you the next one. Now to the question that actually stings. Because by now, the obvious thought is, this should be on every rooftop in the country. It is quieter, safer, and twice as efficient. So why isn't it? The honest answer comes down to two things, and neither one is a secret cabal protecting the power company. The first is plain arithmetic. A real Liam F1 system runs somewhere between $5,000 and $7,000. At the 11-mile-an-hour wind most cities actually get, it produces around 1,500 kilowatt-hours a year. At 15 cents a kilowatt-hour, that is about $225 saved annually, which means the thing pays for itself in north of 20 years. Compare that to a typical rooftop solar setup, which returns its cost in 6 to 8, and for anyone choosing with a calculator, the decision makes itself. The math only flips on a genuinely windy coast or an exposed hilltop, where output climbs and the payback drops under 10 years. Everywhere else, the wind simply isn't worth the wait. The second reason is that even if you want one, the road to owning it barely exists. Solar has a mature world around it, certified installers in every city, standardized parts, permitting offices that have seen 1,000 of them. The Archimedes turbine has none of that. There is no certified installer network in the United States. Most buyers end up doing it themselves, which means understanding three-phase electrical systems, wind-specific charge controllers, dump loads, and whether their roof trusses can even carry a machine that weighs between 200 and 600 pounds while it vibrates for 20 years. Get any of that wrong, and you are looking at a dead turbine, a voided warranty, or a fire. On top of that, mounting it legally often demands paid structural certification, and homeowners associations routinely ban rooftop turbines outright over looks and noise they only imagine. And unlike solar, which several states protect with access laws that stop a town from forbidding it, small residential wind has no such shield. It lives entirely at the mercy of the local planning board, so the technology reaches a handful of technically fearless early adopters and almost no one else. Say you are one of those people, and the wind where you live is genuinely strong. The single most important step comes before you spend $1, and almost everyone skips it. The energy in wind rises with the cube of its speed, which means a site that averages just 20% more wind produces about 70% more power. That is how brutal the math is. So you put up an anemometer, a simple wind gauge, at the exact height and spot the turbine will sit, and you leave it there for 3 to 6 months before you decide anything. If your real average comes in under 10 or 11 miles an hour, the numbers will never justify the cost, full stop, and height matters as much as speed. The turbine has to clear the highest nearby obstacle by at least 10 to 16.